Hey everyone, and welcome. Today we are putting on our detective hats and diving deep into a real cosmic conspiracy. We're not just looking for clues in some old case file, no, we are investigating reality itself. We're trying to figure out why the universe is so beautifully, fundamentally strange. It is a mystery that has stumped the greatest minds for over a century. A puzzle where all the clues seem to contradict each other, and the prime suspects, well, it might just be you and me. So our investigation kicks off with a classic riddle, but with a serious quantum twist. You've probably heard the old question, right? If a tree falls in a forest and no one's around to hear it, does it make a sound? That's all about perception. But we're going deeper, into the quantum forest. And here, the question isn't about sound. It's, if that tree falls, does it even exist as a fallen tree until you decide to check? I mean, before you look, is it somehow both fallen and standing at the exact same time? And yeah, that sounds completely nuts, but that absurd question is exactly what we're here to unravel. It gets right to the heart of the whole mystery. So, how are we going to crack this thing? Well, every good detective needs a plan. So, here's our roadmap. First, we'll check out the scene of the crime and find the quantum glitch, the fundamental bug in reality's code. Then we're going to ask, does looking create reality? Where we explore the wild idea that just our observation is what makes the universe real. After that, we'll look into the cover-up in When Quantum Dreams Fade and figure out how the universe hides all this weirdness from us. Next, it's physics' ultimate showdown, a clash of titans where two of our biggest theories go head-to-head. And finally, we'll open up the cold case files in Ghosts in the Machine to see what mysteries are still keeping physicists up at night. All right, let's get into it. Clue number 1, the quantum glitch, or as I like to call it, the bug in reality's code. Here's the deal. For over 100 years, quantum mechanics has been the most successful, most precise, most mind-blowingly accurate theory in all of human history. It's why we have lasers, computers, and the very screen you're looking at right now. It works so well, it's kind of scary. But for all that success, there's a crack in its foundation, a deep, fundamental flaw at its very heart that we still, to this day, cannot explain. Right at the center of this whole mystery is something called the wave function. Now, don't let the name intimidate you. The easiest way to think about it is as a cloud of pure potential. Before you look at a tiny little electron, the wave function describes all the possible places it could be, all the speeds it could have, all at once. It's not in any one spot, it's just a haze of possibilities, a ghost existing everywhere and nowhere, governed only by the cold, hard laws of probability. But then, something happens. The moment we try to measure it, the instant our detector interacts with it to see where that electron is, poof, that whole cloud of possibilities, that ghostly wave function spread all over the place, it instantly and inexplicably collapses into one single definite reality. The electron picks a spot. The potential becomes actual. It's like the universe literally makes up its mind only when we force it to. And the million-dollar question, the one that gives physicists nightmares, is why? What is causing this collapse? Is it us looking? Is it our equipment? Is it consciousness? This is the central crime we are investigating. Okay, so that leads us right to our next section where we investigate that very moment of collapse. If the wave function is collapsing, something's got to be doing it, right? So who or what is the culprit? In this part of our investigation, we're going to line up the main suspects, the leading theories that try to explain this cosmic crime, and see what they have to say for themselves. And you should prepare yourself because each one of their stories is stranger than the last. Okay, here they are, the three main suspects in the collapse conspiracy. First up, we've got the classic, the old champion, the Copenhagen interpretation. This one basically says, hey, reality is just fuzzy and undefined until you measure it. The act of looking creates the result. The problem? Well, what on earth counts as a measurement? Does a cat count? A camera? A rock? It's just super vague. Next, we have the sci-fi favorite, the many worlds interpretation. This one is wild. It says the wave function never actually collapses at all. Instead, every single possibility happens, and each one splits off into a brand new parallel universe. So there's a universe where the electron went left, and another where it went right. The problem is pretty obvious. Where are all these universes? That's a lot of extra real estate just to solve one problem. And finally, you've got pilot wave theory. This one's kind of sneaky. It says there are secret hidden variables guiding particles on definite paths. And all the weirdness is just because we can't see them. But this idea clashes pretty hard with other big pillars of physics like relativity. So you see, there are no easy answers here. Every solution just opens up a whole new can of worms. To really get a feel for just how bizarre this is, check out this quote. It's like opening a box of chocolates and realizing the flavor changes depending on whether you're hungry. I mean, think about that. In our world, a piece of chocolate has a flavor, period. Whether you're hungry or not is your problem, it doesn't change the chocolate. But in the quantum world, the very act of deciding to measure something, of feeling hungry for an answer, seems to fundamentally change the thing you're looking at. Reality itself seems to bend based on how we interact with it. It's just a total break from everything we assume about the world. And this, of course, leads us to the deepest, most mind-bending part of the whole puzzle. If observation is the key, then what exactly counts as an observer? Does it have to be a conscious person with a brain thinking about the experiment? Or could a simple machine, like a camera, do the job? Or what about something even simpler? What if a single photon just bounces off an electron and carries away some information? Does that count as an observation? We honestly don't have a clear answer. And this is where that hard line between physics and philosophy gets really, really blurry. Okay, so if the quantum world is this chaotic, probabilistic, absolutely bizarre place, why does our world, the big world of people and planets and coffee cups, look so normal, so predictable? That is a fantastic question. It's time we move on to the next part of our investigation and see how the universe hides the evidence. There's a process for this, and it acts like a universal alarm clock, waking quantum systems up from their weird dreams and forcing them into our boring classical reality. This breaks down the process perfectly. Let's just walk through it. Step 1 is what we'll call the quantum dream. A particle is just existing in that fuzzy, fluid superposition where all possibilities are happening at once. Think of Schrodinger's cat, both alive and dead. Then comes step 2. The environment interferes. See, the system isn't really isolated. It's constantly bumping into air molecules, getting hit by straight particles of light, and with every tiny interaction, it leaks a little bit of information out into the world. The environment is basically spying on it. And that leads to step 3, waking to reality. All that information leaking out is like static that just destroys the delicate quantum state. The dream fades, the weirdness vanishes, and only one single classical reality is left. The box is opened, and the cat is now either alive or dead. The weirdness gets washed away. And this is exactly why your coffee cup isn't on your desk and also in the kitchen at the same time. As a big object, it is constantly, relentlessly interacting with its environment. Billions of air particles are bouncing off it every nanosecond. It's being measured by the world around it so completely and so often that its quantum dream state it vanishes almost instantly. It's constantly being forced to wake up into the single stable reality we all know and love. So far, we've been looking at a mystery inside of quantum mechanics. But now it's time to zoom out. Because this quantum glitch, it turns out, is actually a symptom of a much, much bigger conflict. It's a clue that points to an all-out war between the two great empires of modern physics. Get ready for physics's ultimate showdown. So on one side, you have general relativity. This is Einstein's masterpiece. It's the law of the large. It governs stars, galaxies, gravity itself, and it describes space-time as this smooth, flexible fabric like a cosmic trampoline that gets bent by heavy objects. On the other side, you have quantum mechanics, the law of the small. It governs atoms, particles, and probability. It describes a jittery, uncertain world that comes in little packets or quanta. It's a world of jumps, not smooth curves. And here's the problem. They both work perfectly in their own realms. But when you try to use them together, like to describe the center of a black hole, the equations just break. They spit out nonsense. The two theories are fundamentally incompatible. They don't just disagree, they speak completely different languages. So the holy grail for physicists is finding a theory of everything that can unite these two warring empires. And there are two main contenders. First up is string theory. It says that if you could zoom in way, way down, you'd find that particles are actually tiny, vibrating strings of energy. And just like a guitar string can make different notes, different vibrations of these cosmic strings make different particles. An electron, a photon, a quark. It's an amazing idea. The other contender is loop quantum gravity. This one says that space-time itself isn't smooth. It's made of tiny, indivisible atoms of space. Reality would be like a digital screen, made of fundamental pixels. Time itself might not flow, but tick forward in tiny little jumps. Both of these ideas are incredible, but so far we have no way to prove if either of them is right. So we've followed the evidence, we've looked at the suspects. But as you can see, this case is far from closed. In fact, the more we learn, the more mysteries we seem to uncover. So for our final section, let's open up the cold case files of physics and look at the other ghosts that are still haunting the machine. It's not just one mystery, it's a whole bunch of them. Like, is the universe at its core truly random? Or is there a deeper order we just can't see yet? We still have the measurement problem. What truly causes that final collapse into one reality? Nobody knows for sure. Then there's the black hole information paradox. When something falls into a black hole, is the information about it gone forever? If it is, that breaks a sacred rule of quantum physics. And maybe the biggest of them all is the vacuum energy catastrophe. The point is, we're not just missing one little piece of the puzzle, we are surrounded by deep, profound questions everywhere we look. And this really gets to the heart of that whole debate over randomness. Einstein, who helped create quantum theory, could never accept how weird it was. He famously said, "God does not play dice with the universe." He believed there had to be a deeper, predictable reality underneath it all. But his rival, Niels Bohr, supposedly shot back, "Einstein, stop telling God what to do." And for 100 years now, every single experiment we've ever run seems to whisper back in support of Bohr. Maybe he does. It seems that pure, raw chance might just be built into the fabric of reality. Okay, now look at this number. This right here represents the vacuum energy catastrophe I mentioned. Our best theories predict that empty space should be buzzing with a certain amount of energy. But when we actually measure the energy of the vacuum, our measurement is off from the prediction by a 1 with 120 zeros after it. Let me be crystal clear. This is, without a doubt, the single largest, most embarrassing disagreement between theory and experiment in the entire history of science. We have absolutely no clue why our model is so spectacularly, epically wrong. So where does all this leave us? We've explored the glitch in reality, the mystery of observation, the cosmic cover-up, and the war between physics' two greatest theories. And we're left with so many more questions than answers, which maybe that's the point. It leads us to this one final, really provocative thought. Maybe the universe doesn't obey physics. Maybe it is physics, thinking itself into being. What if reality isn't a finished stage, but an active, ongoing process of creation? What if it's all just working itself out as it goes? It's a mind-bending idea, and it leaves us wondering, what new secrets is reality going to reveal the next time we dare to look? Thanks for joining our investigation today.